This is a brief look at organic chemistry and what you could expect when you take organic chemistry in college. And sadly, everything that we do in this unit is probably done in the first week of organic chemistry. This isn't a very mathematical unit at all. In fact, it's very, very conceptual. And that is why the PowerPoint is really, really long. So I've decided to split it into 3 videos instead of one massive video. Just briefly, what is the difference between organic chemistry and biochemistry? And they are 2 different classes in college. Organic chemistry is the study of compounds whose molecules contain carbon. And biochemistry really is the combination between chemistry and biology, looking at the chemistry of living species, like how all of the reactions inside our body work. So what are we talking about here? We're talking about carbon. And remember that carbon has 4 valence electrons, so it forms 4 bonds most of the time. And if you look at that picture, look at each carbon, each one has 4 bonds. And if you have 4 single bonds, you have a tetrahedral shape, sp3, hybridization. They can have 2 single bonds and a double bond, and that would be trigonal planar. They can also be 1 single bond and a triple bond, that would be linear. Most organic molecules have carbon and hydrogen bonds, and there can be other things involved. We'll get to that later. Remember that H only forms 1 bond, so these are what we say are on the surface. And what do I mean by surface? I mean they're out here, okay? And then the carbons form the backbone, and what I mean is there's this backbone of carbon going on. And because of this shape, we get all sorts of really cool possibilities. And this particular drawing has 3 carbons, and it is called propane. So in addition to carbon and hydrogen, you're going to find oxygen and nitrogen and halogens. That would be the fluorine, chlorine, that whole column. Carbon can bond to itself, and so that allows it to create these gigantic, what we call hydrocarbon chains, or sometimes even rings. And then we get into the functional groups, and we're going to do an entire PowerPoint and video dedicated to the functional groups. But those functional groups will determine how an organic molecule can react. Remember that C and H are not very polar, but CO and OH are. Polar regions can dictate how well it reacts with something else, whether or not it dissolves in water or not. And organic molecules have very different functions, which leads to a variety of reactions and lots of possibilities, especially within our body. Just a little bit more on organic molecules, solubility, acid-base properties. Again, most organic molecules are not polar, so they dissolve in nonpolar substances. But if they have polar groups on their surface, then they're going to dissolve in polar substances, or like water, for example. A really good example of that would be if it has an OH group. Surfactants are long organic molecules that are nonpolar, but they do have one end that is polar, and these are used in soaps and detergents. We'll take a look at it in one of our worksheets. And the nonpolar part is the part that extends into the nonpolar medium, like grease or oil, while the other one will extend into water. Makes them pretty fancy. Other functional groups that are important would be the acidic functional groups, like the carboxylic acids. This makes them behave as an acid. And then, of course, we also have basic functional groups like the amines that make them behave as bases. So what do we mean by hydrocarbons? We mean that it is made up of carbons and hydrogens. There are 4 types of hydrocarbons, depending upon the kind of bonds that exist. If you have entirely single bonds, we say alkane, A-N-E. If there's at least 1 double bond, these are alkenes, E-N-E. If there's a triple bond, these are alkynes with a Y-N-E. And then there are aromatic hydrocarbons. And those are carbons attached in a ring, but notice there are single and double bonds. So we've got sigma anti-localized pi bonds going on. A really good example is benzene, and that right there is an example of benzene. Benzene has alternating double and single bonds. And because those double bonds can be where the single bonds are, we usually just draw it as a six, like a hexagon, with a circle in the middle. And that means that they have alternating double bonds, but those locations can differ. These four types are relatively nonpolar, so that means they're not very soluble in water. Their melting points and boiling points really depend upon dispersion forces, and so you have to remember that the bigger the molecule, the more contact the molecules have with each other, the greater the dispersion forces. And hydrocarbons with low molecular weights tend to be gases, moderate weights are liquids, and high molecular weights tend to be solids. This is a very important slide and picture. In fact, you're going to want to pause and take notes. When we name organic compounds, the first thing we have to do is to determine the longest chain of carbons there are, and then that becomes kind of the base point of every name. So if you look at the very first one, CH4, there's only one carbon, and the root of one carbon is meth. In this case, it's methane. If there are two carbons, that would be ethane. 3 is propane, 4 is butane, pentane, hexane, and so on. So you need to memorize these. They're a little bit different than the prefixes we've used in the past, the mono, di, tri. Now we have met, eth, pro, but. And then after that, they're the same, the pentane, the hexane, the heptane, and so on. The other picture shows the difference between the alkanes, the alkenes, the alkynes, and the aromatic ones. Again, alkanes mean that we have all single bonds. ENE, there's at least one double bond. YNE, there's at least one triple bond. And then the aromatic ring is like benzene, where you've got a ring and there's alternating double and single bonds. Here's some other general characteristics of alkanes. If they have all single bonds, then each of those carbons is going to have a tetrahedral shape. And we will get the models out again, and we will look at this, and it'll be pretty evident. There's rotation about that single bond that's very easy, and it happens very rapidly at room temperature. So you have these long chains of alkanes that are constantly undergoing motion, almost like the chain is being shaken. And these alkanes can form straight chain or linear hydrocarbons. When alkanes have 4 or more carbons, they can also start to form branched chains, or what we call side chains or side groups. And this gives it a totally different shape than a line. And again, when we play with the models, you'll see this pretty evident. Then there's something called an isomer. You need to know this word. These are compounds that have the same molecular formula, but the bonding is different. There's a different arrangement. And this, of course, changes the physical properties of them. The more carbon atoms, the more possible isomers there are. And maybe there's a better way to do it, but the best way I have found to figure out how many isomers there are is to just play with the formula and draw out as many different ways as you can. Then there is a term called saturated hydrocarbon. Saturated refers to how many hydrogens you have. If all of the carbons are single bonds, then you're going to have the maximum number of hydrogens surrounding those carbons as possible. But every time you have a double or a triple bond, those form by removing hydrogens. Those are unsaturated hydrocarbons. So saturated just means exactly what it sounds like. If you go stand out in the rain, your clothes will become saturated with water. Your clothes will hold as much water as they can possibly hold. So a saturated hydrocarbon means you will find as many hydrogens as possible around those carbons. And this only occurs when carbon has all single bonds. All right, these are just some examples of isomers. Again, they have the same structural formula, just a very, very different shape, which leads to different physical characteristics. So look at the first two. The very first one is butane. Butane has 4 carbons and there should be 10 hydrogens. There is a little formula. When you have all single bonds, the number of H's is twice the number of carbons plus 2. So if there's 4 carbons, double that, you get 8, add 2, you get 10. So 2-methylpropane, if you go and stop this and count, you're also going to have 4 carbons and 10 hydrogens, but a very, very different shape. In butane, you've got a chain of 4 carbons, and in propane, you have a chain of 3 with the 4th one coming off that middle carbon. That's what we call a side chain group. And then the last 3 are also isomers, but obviously they're very, very different. So here you've got pentane. So you have 5 carbons, double 5, add 2, you're going to have 12 hydrogens. So go ahead and pause the video. Look at the 2-methylbutane and the 2,2-dimethylpropane, and you will see that you have the same number of carbons and number of hydrogens, but very, very different molecules. While we don't have math in this particular section, we do have nomenclature, and that means naming. A little bit of problem solving here, but it's kind of fun. Common names begin with N. We don't use this very much in this class. When there's branching that occurs, you might have other prefixes like iso and neo. We really don't use this very much in this particular class. But organic molecules have 3 basic parts to their name: a prefix, a base, and a suffix. And the prefix has to do with the substituents. Those are all those side chains. They come first. And then the base really has to do with the number of carbons in your chain. And then at the very end is the family. And the very end name tells you what's going on. So let me give you a quick example, and we'll do a lot of these in class. The first thing you want to do is you want to find the largest carbon chain there is. And this can be tricky. I really recommend that you draw this out and then use a pencil to kind of highlight your chains. So in this particular one, you'll notice, let me draw on here, that your largest chain is right here. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3. You could have also gone this way, to be honest with you, and you'd still get the same answer. It really doesn't matter. Point is, find the longest chain of carbons. So we have 6. So the first thing we're going to do is start with that base. 6 goes with hex. So we know we have hex. And they're all single bonds, so it's probably going to be hexane. Then what you need to know is that I'm going to go ahead and erase this and just show you again something here. So let's say we go with this chain right here, okay? We need to number these carbons, and you want to number them, this is very important, so that this chain, this little side chain hanging off here, is on the lowest numbered carbon. What do I mean by that? If I would have started with number 1 here, 1, 2, 3, 4, then this would have been 5. That can't happen. We want this group here to be on the lowest number. So we're going to start numbering right here, and that way this carbon right here is a 2. Okay? So we have the base name of hexane. And we need to then label this side chain group. And we're going to talk about this on the next slide. This side chain group is called a methyl. If you would have added an H, you would have had methane, 4 hydrogens and 1 carbon. You remove the ane and add an ethyl or an YL on, and methane becomes methyl. So this is actually 2-methylhexane, but we'll talk about that a little bit more in the next slide. Let's get a little bit more into the rules for naming organic compounds. And we'll spend a lot of time on this. You'll get a lot of practice. And believe it or not, it gets pretty easy pretty quick. Again, number the number of carbon atoms in the longest chain. Count, don't always assume you found the right one to begin with. And then start numbering them nearest one is the substituents, nearest one of those groups that have been added on. And I really find it better that if you draw it out and use a colored pen or pencil or highlighter and sketch out that long chain, then you can see those pieces that are stuck to that chain, and then you can name those substituents. And here's how you do it. So let's say you've got just 1 carbon. The group hanging off has just 1 carbon. Well, that's going to start with methane, and that's going to become methyl. What if you've got something hanging off the chain and it's got 2 carbons? Well, its group is going to be called ethyl. If there's 3 carbons, it's going to be called propyl. 4 carbons, butyl, and so on. We're probably not going to do the isopropyl or the tert-butyl very much in here, but you will if you take organic chemistry. So you begin the name with the number or numbers of carbons to which each substituent is bonded. What does that mean? So you've got this chain and you have a methyl group hanging off. You have to tell us where that methyl group is. If I just simply say, could you draw me methylhexane? Well, that's pretty easy to draw a chain of 6 carbons. But where am I putting that methyl? I'm sorry. Could you draw me 3-methylhexane? Oh, that methyl is going to go on carbon number 3. So you have to state that. If there's more than one substituent, what if you have a methyl and an ethyl? Well, who goes first in the name? Alphabetical order. So the ethyl will go before the methyl. Now, as if that's not complicated enough, what if you've got 2 methyls and an ethyl? Well, we have to state that. And so the methyl becomes dimethyl. And then you also have to tell me where they are. So maybe it's, 2-ethyl 3,4-dimethyl heptane, for example. I know, it sounds complicated, but it's really not that bad. Let's try and name one on the next slide. Let's take a look at how to name this one. Now, the first thing you need to do is find the longest chain of carbons. And this one's pretty obvious. If you go right through here, you're going to have the longest chain of carbons. And we have 1, 2, 3, 4, 5, 6, 7. That's where you start. So we know we're starting with the word heptane. And it's going to be heptane because there's all single bonds. I'm just going to write in cursive here. I apologize. Woo. Now, by drawing that line in there, you should notice that group and that group are not part of the original chain, okay? So we need to identify those. Those are those substituents. Well, there's only one carbon in each of them. So we know we have methyl groups. And there are 2 of them. So we know this is going to be dimethyl. Dimethyl. Again, I apologize. I don't have a mouse and I'm writing in cursive. Now, if I said, please draw me dimethylheptane, I know you would have no problem drawing 7 carbons and adding all the H's. But where are you going to put those 2 methyl groups? We have to say where we're going to put them. And that is based on the number. So if we start numbering right here, this would be carbon 1, 2, then 3, and then this would be 4. So this would give us 3,4-dimethyl. But what if we started numbering from here? Then we have 1, 2, 3, 4, 5. So do we want this to be 3,4-dimethyl or 4,5-dimethyl? Always go with the lower number. So this is going to be 3,4-dimethyl, heptane. And as far as like the dashes and whatnot go, I'm not going to be too particular on that. To be honest, I've been out of this for a long time. I don't always put them in correctly, but I am looking for 3,4-dimethyl heptane. Those are the key things you need to know. Not only can hydrocarbons make long chains, but they can also make rings, and we call those cycloalkanes. Cyclo, circle. We can draw them one of 2 ways. One way is to actually show the carbons and hydrogens, and another way are just using lines. And it is implied that each vertex is a carbon. And you would see, like, right here is a C, so we know over here is a C and over here is a C. Well, each carbon can make 4 bonds, so it's implied that the other 2 bonds are hydrogens. We just don't show all that. Personally, I like the more detailed version. I think it makes more sense, but sometimes they just do this. But anyway, these are not the same rings as benzene because benzene had those alternating double bonds in there. These are just all single bonds. The carbon rings that have 5 carbons or less start to become strained. So which one is going to have the most strain, which one's going to be the most reactive. It's going to be your triangle. And when we actually make models, I'm going to ask you to try and make a ring with 4 carbons and then a ring with 3. And you're going to see that it's pretty much impossible to do with our models. And that'll give you a better idea of just how much strain there is. So the fewer carbons in your ring, the smaller the ring, the more reactive they are going to be. It's almost like stretching that rubber band and it just wants to snap. Alkanes only have single bonds and carbon and hydrogen bonds, so they're very, very unreactive. And this is because the CC and the CH bonds are pretty strong and there's no polarity going on. They are, however, very combustible in air, which is why we use hydrocarbons as fuel. So these reactions are actually very exothermic. So far, we've only talked about alkanes, and those are chains of hydrogens and carbons that only have single bonds between the carbons. Well, what about alkenes, alkynes, and aromatic hydrocarbons? These have either double or triple bonds or delocalized pi bonds. Those would be the aromatic ones like benzene. Because there's double and triple bonds, we're going to have less hydrogens than are possible around all the carbons. So they're not saturated, they are unsaturated hydrocarbons. And all of these are more reactive than the alkanes. So let's look at the alkenes. When you see ENE, what we're talking about here is at least one double bond between the C's. The simplest one would be ethene, 2 carbons attached with a double bond. They can have isomers, so that means you're going to have the same formula, but different geometrical shapes, different bonding, and of course, different properties. Again, the name is based on the longest continuous chain of carbons that has the double bond. We're going to change the ending to ENE. So if there were a double bond in between 2 carbons and there were 3 carbons altogether, propane becomes propene. And then we have to state where that double bond is. We're going to use a number as a prefix that designates the double bond nearest the end of the chain. So again, you go with the smaller number. Always, always number the carbons starting with the end that is closest to where that double bond is. So let's say you have butene. You have 4 carbons. If the double bond is right after the first carbon, then it's on carbon number 1. So we say it's 1-butene. If it were after the second, it would be 2-butene, and so on and so forth. Let's look a little bit more at alkenes. What if there's 2 or more double bonds? Well, again, we still need to state where those double bonds are, but then we're also going to use a prefix to explain how many double bonds there are. So diene would mean 2, triene would mean 3. So if you've got that particular example there in the bullet, it's got 5 carbons, and we have a double bond on the first carbon and the fourth, so we would say 1,4. Penta, diene. 1 and 4 tell us where the double bonds are. Penta means there's 5 carbons. Di means 2. Ene means double bonds. Again, 5 carbons, 2 double bonds. One's on the 1, one's on the 4. Again, geometric isomers, these have the same formula, the same bonds, but they have a different spatial arrangement. And we will look at this. And this doesn't happen with the single bonds, but it does with the double bonds. So take a look here. In this case, we've got this pattern right here, right? Now this only has 3 carbons, so this is going to be a propene. And you've got this methyl group hanging off here. So this is methylpropene. But what happens when you have 4 carbons in a row? Well, there's no methyl group, it's just hydrogen. So this is just going to be straight up 1-butene. Double bond is on the carbon number 1. Now this is where it gets to be a little bit more fun. If you've got this chain here, you've got the double bond smack in the middle of all those carbons. Well, even though this isn't a methyl group, it's part of the chain. Do you see how those methyl groups are on the same side of the molecule? When they show up on the same side, because right here would be trigonal planar if you look at your geometry. When they're on the same side, we say cis. When those methyl groups are opposite sides, we say trans. So this one is cis-2-butene and this one is trans-2-butene. And believe it or not, they actually have different physical and chemical properties. Then we have the alkynes, and these are unsaturated that contain at least one triple bond. Again, they're unsaturated because we don't have as many hydrogens around all the carbons as possible. These are very reactive compounds. And to name them, again, you identify the longest carbon chain. You have to change the ending to YNE, and you have to consider any functional groups, or you have to consider any other side chains that might be attached. We know that double and triple bonds are very reactive, and so we get to have some fun chemistry with them. An addition reaction is where we add something, for example, like a Br2 molecule, and that actually breaks the bond, and whatever it is you're adding becomes embedded in that overall molecule. So if you add hydrogen to an alkene, it's just going to turn it into an alkane. Pretty boring, pretty basic. We call that hydrogenation because you're adding hydrogen. It doesn't happen readily, so we do need to raise the temperature or use a catalyst, and a lot of times you will see that written above the arrow. Lots of things can be added to alkenes and alkynes. Again, if you add hydrogen halides, so that would be like HCl or something, or HBr, both the H and the Br become embedded in the molecule. And so if you look at this very first thing here, there's your double bond. Notice the double bond is gone, and that H and the Br become embedded in the molecule. You can also add water, and that is going to, again, put in an H and an OH. It does need to be catalyzed by sulfuric acid. And here's just some other examples. Here's a triple bond. Let's add a chlorine molecule. Now notice the triple bond becomes a double bond in this case. And there's a chlorine over here and there's a chlorine over here. So this would be that trans product we talked about because you've got the CH3s on opposite sides. If you add another chlorine, then the double bond becomes a single bond, and you get rid of it all. By the way, this also works for Br2 and I2, and it really depends. Sometimes alkenes are more reactive than alkynes and vice versa. It just depends on the chemical. The last slide for this particular PowerPoint is going to talk about aromatic hydrocarbons. So aromatic simply means that you have a circle, you have a ring, but now we've got double bonds going on in here. And again, benzene is the best one that we can come up with. They've got a few different examples of benzene. This is what it actually looks like. This is how we draw it without the carbons and hydrogens. But again, this actually has resonance. Those double bonds could actually be here, here, and here instead. And so to show the resonance, we just draw a circle on the inside. And then here are just some examples of different reactions you can do. I'm just not going to get into them all here, but they don't really undergo addition reactions. We do what's called a substitution reaction, where one of those hydrogens is removed and replaced with a different group. And of course, it totally changes the physical and chemical properties of the substance. So kind of fun.